In this video, we're going to talk about free fall and the acceleration due to gravity. All unsupported objects are going to fall to the earth with the same acceleration. We call this acceleration the acceleration due to gravity, where gravity is the gravitational force. It's denoted by the letter G. It's a lowercase g, not a capital G. And here you can see G is equal to 9.8 meters per second squared. Notice there's no vector sign over the G. That tells us that this is a magnitude. If I wanted to write this as a vector quantity, I would write G with a vector sign is equal to negative 9.8 meters per second squared J hat. Okay. Notice the difference. Here, no vector sign. Here, no direction. Here, there is a vector sign. Notice that I have to give it a direction. Okay? Keep in mind that all objects will accelerate towards the Earth at the same rate. So in this case, we're going to treat G as a constant. This video is kind of cool, but you're not going to be able to hear it from my video system here. So what I'm going to do is I'm going to go ahead and access this off of YouTube, and I'm going to upload the link for you. So if you want to pause this video and look at the other video on Galileo's experiment on the moon, it's very cool, and you should do that. You don't have to do it now, but you should take a look at it sometime after you get done this video. Okay, so let's look at free fall and what it means. So here we're going to start with an object that's thrown upward with an initial velocity v0. And then we want to know what happens when it goes up. So let's go ahead and click on that question. It's going to slow down, and that's because the acceleration due to gravity is negative 9.8 meters per second squared J hat. Okay, so then what happens at the top? At the top, it's going to stop momentarily. Now this is the trick. Everyone always says to me, oh, Dr. H, that means that the acceleration is 0 at the top. No. The acceleration is not 0 at the top because acceleration is the rate of change of the velocity. Is the velocity changing? Yes. Yes, it is. Is it momentarily 0? Yes. But does it stay 0? Does the ball or the object stay hovering in the air? No, it doesn't. It actually turns around and starts falling again. And so we still have an acceleration at the top. And that's going to be, that's right, negative 9.8 meters per second squared J hat. Okay, so what happens on its way down? Well, it speeds up because it's now going in the same direction as the acceleration. It's going down. And so it's going to accelerate downward at a negative 9.8 meters per second squared J hat amount. Okay? So what happens at the very bottom when it lands? Guess what? It's going to have its original magnitude of velocity. So what I'm going to do is I'm going to put in here the word magnitude, because guess what? It's not the same velocity, is it? And the reason it's not is because it's changed its direction. So it's the original magnitude of the velocity, okay, but opposite direction. So I'm going to write opposite here. You'll have to excuse my mouse handwriting. And because I'm having so much trouble with my mouse, I'm just going to abbreviate. So it's going in the opposite direction. Okay, so let's look at going up. When we're going up, we start out with some velocity v0, and we have some acceleration. If we take this amount away from our velocity, we have v1. Okay, so after 1 second, it decreases, this decreases by this amount, and we end up with this. Okay, after 1 second, this is what we have. Okay. Now, in order to find out what happens after 2 seconds, we subtract this from this, and we end up with this. And there we go. After 2 seconds, we have this much. We subtract this amount from this, and what do we end up with? 0. Okay? So basically, if we're starting at, let's say, 30 meters per second, after 1 second we have 20, after 2 seconds we have 10, after 3 seconds we have 0. Because we're effectively subtracting 9.8 or roughly 10 meters per second every second. Okay, so what do we do on the way down? Well, if we start at some velocity, initial velocity at t equals 0, then we add this amount to here, and we get twice as much, okay, after 1 second. Now, if we add this amount to the original, or add this amount to this, we end up with this, okay? If we add this amount here, after another second, we're going this much more, okay? So we're effectively taking this and, oh, they've locked it. We're taking this amount and adding it here, and that is our new velocity. Okay, so now let's look at graphs. When we talk about free fall and we're talking about motion on a graph, anytime you throw an object straight up in the air, your velocity time graph is going to look like this, okay? And I'm going to add a few things because this isn't quite right. We need to have the direction, right? This above the x-axis, it's plus j hat. Below the x-axis, it's negative j hat, okay? When you don't put that information, it becomes kind of iffy. Like, what does this mean? What do I mean when I have v without a vector sign? Is it a vector or is it a scalar? Well, it's a vector. So we're going to add units to the 0 as well, because 0 seconds is different than 0 meters per second. So we're going to add some units and a direction. Okay, so notice here we start at maybe 3 meters per second thrown upward. After 1 second, it decreases. After 2 seconds, it decreases. After 3 seconds, notice that it's 0. Now, after 4 seconds, look what happens. It's now going in the opposite direction. So again, it's the original magnitude of the velocity, but the opposite direction. So I'm going to put here speed, because it's not the original velocity, it's actually the magnitude of the velocity that stays the same. And in this case, we can call that the speed of the object. So original speed, but opposite direction. And that means it's a velocity. Okay, so now we're going to get into the multiple choice and free response problems. I'm going to ask you to pause if you need to. If you don't need to, if you've already solved the problems, then you can just keep playing the video. Okay, so a ball is dropped from rest and falls. Again, we're going to ignore air resistance because we're going to call this free fall. Which is true about its motion? Is it A, constant acceleration, B, constant velocity, C, decreasing velocity, or D, decreasing acceleration? Okay, so let's take a look at the answers. Hopefully you chose A, the acceleration is constant. Remember I told you it's the acceleration due to gravity. Okay, now these are free response questions. So what you're going to do is after I read the problem, pause the video, solve it, and then start to play again. An acorn falls from an oak tree. You note that it takes 2.5 seconds to hit the ground. How fast was it going when it hit the ground? Okay, so let's go ahead and take a look at the solution. Now, you may be saying, wait a minute, Dr. H, you never taught us these formulas. But I did, and I'm going to show you where this came from. Remember I told you the definition of acceleration is equal to the change in velocity divided by the change in time, or the elapsed time. Well, what's delta V? It's V final minus V initial, or V minus V naught. And so if you manipulate this algebraically, you can get this equation. Okay, so substituting in our numbers, we end up with 0 meters per second j hat, and the acceleration due to gravity is negative 9.8 meters per second squared j hat times the 2.5 seconds, and that ends up giving us negative 24 meters per second j hat as our answer. So this tells us that we're going down. Okay, a rock falls off a cliff and hits the ground 5 seconds later. What velocity did it hit the ground with? Again, it's falling, so we assume that the initial velocity is 0. Okay, so let's take a look at the solution. Again, we're using the same formula, so I'm going to go ahead and fix it and put the vector signs. Oops, sorry, that's j hat. J hat. Okay, so you should have ended up with negative 9.8 meters per second squared j hat times 5 seconds. Now, if you ignored this and didn't put this in, please be careful. On the AP exam, they want you to show all your work. So they actually give you a point for writing the equation, and you actually get a point for substituting and having the correct number of sig figs. A lot of times, though, they do not give you any points for the correct numerical answer. So when it comes to the AP exam, they're more interested in your steps and what your reasoning is, your thought process, than they are the numerical answers. So please make sure you're writing everything out when solving these problems. Okay, a ball is thrown down off a bridge with a velocity of 5 meters per second. What is its velocity after 2 seconds? Okay, so let's take a look at the answer. We're going to use the same formula that we've been using. V is equal to V naught times, plus AT. We're going to put negative 5 meters per second j hat as the initial velocity. We then have the acceleration times 2 seconds, and that gives us an answer of negative 24.6 meters per second j hat. Now, is this the correct number of sig figs? No. No, it isn't. This one only has 1. This one only has 1. You should have 25 as your answer. Now, you may be saying, wait a minute, Dr. H, didn't you just say that this one was 1 and this one was 1? Why isn't this 1? Remember that you're adding these two numbers together. So when you multiply this, this isn't a constant. This is a constant. So probably you could say the answer is going to be negative 30 or negative 20. Again, that's why I don't use single-digit numbers for problems. It just makes it unclean as far as the sig figs are concerned. So I would say just make it 25 meters per second j hat. In other words, keep with the precision of the given information. Okay, so that ends this video on the acceleration due to gravity and also free fall problems. In the next video, we'll talk about solving problems.